The next thing we're going to talk about is a special kind of probability distribution known as the binomial probability distribution. Now, the last example we ended with in the previous section is kind of a nice example of this. We had this person, Jill, who plays poker, and the key factor with this is that really, we had this one guy who played poker and he could have like 0 wins, 1 win, 2 wins, 3 wins, 4, whatever. For this person, Jill, we basically distilled it down to there's just 2 outcomes we care about. Did she win? Did she lose? And that's kind of the essence of a binomial distribution. It's got the prefix bi in it. Bi meaning 2, like a bicycle having 2 wheels, for instance. Binomial distributions are where there are 2 possible outcomes. You can win, you can lose. You can succeed, you can fail. It could be male, it could be female. It could be heads, it could be tails. It could be up, it could be down. There's 2 possible results. So this is an example of a discrete probability distribution table. We saw a lot of those before. And so a special kind of discrete probability is a binomial distribution. In this case, we're going to have the same event repeated n times. And the binomial distribution refers to the probability of getting x number of outcomes. So like if I'm going to flip a coin 10 times, n would be 10, the total number. And then I could have a binomial distribution of 0 heads, 1 head, 2 head, 3 head, all the way up to 9 head, 10 head, something like that. So some terminology: a trial is an experiment. An example of this might be like a flip of a coin. There's multiple possible outcomes, but there's really only one that we're interested in. And so the outcomes of the 2 trials are independent. We will refer to the trial results. The ones that we're interested in will be a success. Anything other than that will be a failure. So even if we're in a situation where there's not 2 possible results, we're going to try to distill the possible outcomes down to success or failure. So for instance, if I'm playing a game with dice and all I really care about is getting a 1 or a 2, then the probabilities for 1 and 2 together, those would be defined as success, because that's what I want. And then all the other possible outcomes, if I roll a 3, if I roll a 4, roll a 5, or roll a 6, those would be classified as a failure. So P is going to denote the probability of success, Q is going to denote the probability of failure, and the 2 probabilities, P and Q together, should add up to 1. Alternatively, Q can be found by doing the complement of P, 1 minus P. A binomial experiment, we're going to repeat any trial n times, and we're interested in how many, the number of successes out of the total n that we get. And so x is going to be the number of successes. So here is a formula that we can use. So we're going to use combinations that we saw before in chapter, 5. So you do n trials total, choose x successes, and then you'll do the probability to the x power, and then the complement, the chance you fail, to the n minus x power. And then these are some handy formulas. If I were you, I would definitely jot these down somewhere. The mean is n times p. The variance is n times p times q. This, by the way, is why the variance is a thing. Like, it makes the formulas nicer in a lot of higher level statistics. So the variance is a thing just because, like, the formulas tend to be prettier. And then you just know in the back of your mind, oh, if it says standard deviation, square whatever on earth that is, and there you go, that's the standard deviation. So those are some useful formulas to have at your disposal. You got the mean, you got the variance. All right, so a standard 6-sided die is rolled 5 times. Let X represent the number of rolls that result in a 1 or a 2. So describe the distribution of X by completing the table below. So here's what we're going to do. Let's see. So N is the total number of times that this is happening. So N is 5. P, the probability of success. Well, let's see. So a result of 1 or 2 is a success. That means that there is a 2 out of 6 chance that I will be successful, which is another way of saying 1/3 or 0.33. That's 0.33 repeating. Q is going to be 1 minus that. So that's basically going to be a 4 in 6 chance, which is 2/3. And that's going to be 0.66 repeating, or you could round that off as it's approximately 0.67. So what we need to do is we need to do capital P of X, as opposed to this over here, which is little b. Capital P of X, that's going to be equivalent to 5C X times, and then we're going to do 2 out of 6 for P. We're going to do that to the X power, and then we're going to do the 4 out of 6 chances that we fail. And we're going to do that to the 5 minus X power. So let's break out the handy dandy calculator here. So I'm going to go to my Y equals menu. And let's see, we're going to do 5, go to math, go over to probability and pick NCR down there. So 5CX, arrow over to get out of this because we're done with that. And then what we're going to do is we're going to do 2 divided by 6. Yes, I'm well aware that that's 1/3 if you want to do 1 divided by 3. Fun fact, the calculator actually doesn't care whether or not you reduce the fraction. So we're going to do 2 out of 6 raised to the X power, arrow over to get out of there. And then we're going to do the 4 out of 6 chances that we fail. And then this power, all in the power, we're going to have 5 minus X. So all of that 5 minus X is in the power. I got the power. Sorry. So what we're then going to do is we're going to call up the tables. So we're going to do, that's in blue right here for mine. So I'm going to do second for the blue key. So we're going to do second, go to the table. And then if we arrow up here, so there's an error, but that's okay. So here are all the different probabilities that we can have. So you've got what? We'll round these off. 0.13, 0.33, 0.33. Let's go ahead and start writing these down here. Let's see. This one was 0.13. These two were 0.30. This mouse. 0.33. There you go. All right. Writing with a mouse is so annoying. But anyway, 0.33. And then what else do we have? That's going to be 16. 0.04, 0.004. All right, so this is 0.16. This is 0.04. This is 0.004. With rounding, those values are probably not going to quite add up to 100, but that's essential. That's the distribution table. Find the expected value of X. So the mean, which is this one, it looks kind of like a cursive U. So the mean is going to be n times p. So the number of trials is 5. The probability of success is 2 out of 6. So if you do 5 times 2 divided by 6, let's go second quit and get out of here. 5 times parentheses 2 divided by 6 is going to give you 1.67. So you can expect just under 2 out of those 5, a little under 2 out of those 5 rolls to be successes. So 1.67. So that would be the expected value. Then they say find the standard deviation. All right, well, let's first find the variance. So sigma squared is NPQ. So that's going to be 5. Whoa! All right, this mouse. 5 times 2 out of 6 times 4 out of 6. Let's see what that is. All right, so 5 times 2 divided by 6 times 4 divided by 6. That is 1.1 repeating. 1.11. And so then the standard deviation is just the square root of that. Oh, mouse drives me nuts. All right, so we're going to do second x squared to do square root. We're going to do second negative to get the answer. So square root the answer that you just got, which is 1.11. And you do that and you get 1.05. That'll be the standard deviation. And just watch with rounding these. With the homework problems, don't round decimals until you get to the very end. Use the answer function in the calculator and just round to however many decimal places it's going to ask for. So just be cautious when you're rounding. But there you go. So there's the mean. This one is the variance. You square root that, you get the standard deviation. Let's see. We can calculate these with some calculator functions. So you can find both binomial PDFs and CDFs if you go to second and then bars. That'll give you the distributions menu. Option 0 is binomial PDF. Option A is the binomial CDF. This is very crucial here. If you're finding the probability of x equaling x, that's when you want the binomial PDF. If you want the probability where x is less than or equal to x, that's where you're going to need the binomial CDF. And then the key values that the calculator will need are it needs n, the total number of trials, it needs p, the probability that you succeed, and it will need x, how many successes you are looking for. So n is the total number of times you do it, p is the probability you succeed, x is the number of successes you are going for. So what do we have here? Widgeco manufactures widgets. It is known that 1 out of every 50 widgets that they make is defective. A batch of 1,000 widgets is checked for defective widgets. Find the probability that the number of defective widgets in the batch is, first one is equal to 20. All right, well, let's start with information we know. So the probability that it is defective, so we're basically saying the probability that we have defective widgets. So even though they're defective, that's what we're going to call a success, quote unquote. Just so you know, in probability, success is not necessarily a good thing. It's just whatever we're describing as the outcome we're looking for. I used to work in the private sector for a life insurance company, and we would often be interested in knowing people's mortality rates, which is a kind of polite way of saying, what is the probability that a person will die? And for the purposes of the calculations we were doing, death was a success. Now, most people, I'm sure, would not consider death to be a success. So just don't necessarily think that success means a good thing. Just putting that out there. All right, so probability, that's going to be 1. Oh, let's not do the highlighter, please. Thank you. 1 out of 50. And if you do 1 divided by 50, that is 0.02, which is a lot friendlier to use as a decimal. The total number of experiments we're going to do is 1,000. So that, my friends, is going to be n. N is going to equal 1,000. And so then the x value is going to vary depending on these conditions here. So what's the probability it's equal to 20? So we got the probability that x equals 20. So for this, what we're going to do is we're going to do the binomial PDF, because there's really only one value we're interested in. We're going to give the total number of trials, which is 1,000. We're going to give the probability of success, which is 0.02. And then the number of outcomes that we're interested in, the x, that is going to be 20. So let's break out the friendly neighborhood calculator here. The vars key is right here. It's right next to clear, just under the arrow pad. So we're going to, and actually what we're looking for is distributions. We're talking about probability distributions. So you see right above it, it says distr, which is for distributions. So we're going to do second vars. We got to go all the way down here. And actually it looks like my calculator is slightly different. Anyway, the one you want is binomial PDF. Wherever it is, pick it. All right, so there's binomial PDF. Number of trials, there are 1,000 of them. The probability of success is 0.02. The x value is 20. So actually, this is even more straightforward than the way the TI-83, because what I wrote down is what you would type into a TI-83. But anyway, let's see, paste. Okay, so it's going to type that all in for you. How about that? Go ahead and hit enter. 0.0897. There you go. So the answer is 0.0897, which is roughly 0.09 or 9%. So there's a 9% chance that you will have exactly 20 defective widgets. What's the probability is equal to 25? Well, this is going to be much the same. You're going to do the probability of x equaling 25. So again, we're going to do the binomial PDF here. So let's go second vars. We'll do alpha A. That's where my binomial PDF lives. We're still doing 1,000 trials. We still got a probability of 0.02. This time, the x value we were after is 25. So this time, it's down to 0.0446 if you round that off. 0.0446. So roughly a 4.5% chance that will happen. Okay, so what is the probability that it is less than 20? All right, so here, just so you know, the binomial CDF, it is less than or equal to. So here, we're saying the probability that it is less than 20. They do not say it is less than or equal to 20. They say it is less than 20. Well, since your options are either 19 or 20, because this is discrete, this would actually be another way of saying the probability is less than or equal to 19. So we can have everything up to and including 19. And then this is going to be a binomial CDF, because this is cumulative. So instead of finding all these values individually, we're going to use the CDF function, and it's going to add all of the individual probabilities up for us automatically. So this is going to be the binomial CDF, and we're going to have 1,000. We're going to have 0.02 for the probability, and then the number of interest is 19. So let's grab the calculator here. We're going to go second bars. Mine is alpha B. Binomial CDF. 1,000 is the number of widgets we're testing. The probability is 0.02, 1 divided by 50. The X value is 19. That is 0.4694. So there's roughly a 47% chance we will have less than 20 defective widgets. Okay, what's the probability? It's between 10 and 30 inclusive. All right, this one's kind of a tricky one. So what do you want? You want the probability that 10 is less than or equal to X, which is less than or equal to 30. That's another way of saying take the probability of X less than or equal to 30, and then we're going to subtract the probability of X being less than or equal to 10. Because this is basically saying I want everything between 10 and 30. So the way you find between 10 and 30 is you say, all right, give me everything from 0 to 30, and then take away everything from 0 to 10. And then what's left, what will be left is everything. And actually, let's see, we actually want that to be 9, because we do want to include 10. So actually we need to do 0 to 9, because by doing less than or equal to 10, it is going to remove 10 from our count. We do want 10 to stay there, which means that we're going to do everything from 0 to 9 and get rid of it. And what's left is going to be everything from 10 to 30. So what we're going to do is we're going to have to do this in stages. We're going to do the binomial CDF for 30. So the binomial CDF for 1,000, 0.02, and 30. Minus the binomial. It'll take me less time to do it in the calculator than to write all this nonsense with a temperamental mouse. Let's see, binomial CDF 1,000. Let's see. I should really get a stylus one. I should get a computer that can use a stylus. But anyway, this one is 9. All right, there we go. So let's find each of those, and then after we get those decimals, we can subtract them. So we've still got 1,000. We've still got 0.02. We want 30. All right, so tell us what that is, calculator. That is 0.9874. So what I'm going to do is I'm going to do the store key and call that alpha A. So that's the first value. And then we're going to do this all over again. So we're going to do second vars. We're going to go down to alpha B here. That's where binomial CDF lives. Trials is 1,000. P is 0.02. And then this time we're doing 9. So that is 0.0047. So then if we do alpha A minus second negative, the answer. So we're going to do this decimal from back here and then subtract the answer I just got. And if you do that, you get 0.9827. And again, you want to round at the very end. 0.9827. Okay, so you're almost guaranteed to have the number of defective widgets somewhere between 10 and 30 inclusive. Find the expected value. Okay, well, if we find the expected value, that might illuminate why that is. The expected value is n times p. The number n was 1,000. The probability p was 0.02, 1 divided by 50. So if that's what this is right here. So if you do 1 divided 50, that is where 0.02 came from, in case you missed it. Let's see. So we need to do 1,000 times 0.02. That is 20. So hey, what do you know? The expected value is 20. So then that's probably why if you look from the range 10 to 30 and 20 smack dab in the middle of that, that's why you're almost guaranteed to get a defective widget somewhere within that range of numbers. What's the standard deviation? Well, the variance, which is sigma squared, that is n times p times q. We know n, that's 1,000. We know p, that's 0.02. If you do 1 minus p, 1 minus 0.02 is going to give you 0.98, because this decimal, because the two decimals should add up to 1. So if we do that, that gives you 19.6. Now remember, that is the variance. And then if you do the square root of 19.6, that will tell you the standard deviation. So the square root of 19.6 is 4.43, roughly. All right, so then they say, find the probability that the number of defective widgets will be within 1 standard deviation of the mean. So what's that mean? Well, you're going to take the mean, which is 20. You're going to subtract the standard deviation once. And then you're going to add the standard deviation once. And that will give you a range of numbers to look at. So adding is going to be the easier of the two. That's 24.43. And then what is 20 minus that? That is 15.57. So what we want is the probability that 15.57 is less than x, which is less than 24.43. So you've got to go to the nearest whole number with each of these, because since this is a discrete distribution, we cannot have decimal values. And we're going to need to narrow this in here, because if you go all the way up to say 25, you're actually going to be beyond one standard deviation. So we have to do a more conservative estimate here. And then this 15.57, we're actually going to have to go up to 16 here. So we're going to do 16 is less than or equal to x, which is less than or equal to 24. And so then the way we would find that is we would do the probability that x is less than or equal to 24 and subtract the probability that x is less than or equal to, we do want to include 16, so that means that we're going to do 15 as our cutoff for the bottom end. Kind of like last time how we wanted to include 10, so we went down to the 9 to find our cutoff. These are both going to be binomial CDFs. So we're going to do much the same thing we did last time. We're going to do second vars. Alpha B is where mine is located. You can scroll down with your arrow keys to find it. Let's see, there's still 1,000 trials. The probability is the same. For the first one, we want to find 24. And if we do that, that is 0.8455 roughly. I'm going to hit the store key and I'm going to do alpha A again, store that in variable A and save it for later. Now we'll do this all over again. We're going to do second vars, go down to where binomial CDF lives. There it is, pick enter. That's the same, that's the same. This time we were doing, what was it? 15, yes, 15. So 15, and you work out what that is 15.39% roughly. So then we're going to do alpha A minus second negative for the answer. So do this 0.8455 minus 0.1539, and that's 0.6916, roughly 69%. So this one is 0.6916. So there's about a 69% chance you are within one standard deviation of the mean. All right. Only about 70% of donated human blood can be used. The remaining 30% cannot be used because of various infections in the blood. So suppose a blood bank has 10 newly donated pints of blood. Find the probability that 2 or fewer pints will be unusable. Okay, so let's see. So we're interested in whether or not something is unusable. So P is going to be defined as unusable. And then they actually go ahead and tell us what Q is as well, which is 70%. So 30% as a decimal is 0.30 or 0.3. The total number is 10, so this is your N value. So we want the chances that 2 or fewer, so this is the probability that X is less than or equal to 2. So since it's less than or equal to, this is going to be a CDF. All right, so let's figure out what this is. We have N, we have P, X in this case is 2. We know it's a CDF. So we're going to go to second vars. Alpha B is where my binomial CDF is. The number of trials is 10. 0.3 is the success, as in it's unusable blood. The X value we're interested in is 2. So that probability is 0.3828. So that's what this is, 0.3828. What's the probability the number of unusable pints will be more than 5? Okay, well, let's think through what this means. This is the probability that X is greater than 5. That would be the complement of 4 and below. Or no, I'm sorry, that's the complement of 5 and below, because 5 is currently not being included. So this is 1 minus the probability of X less than or equal to 5. So we're going to do the binomial CDF at 5 inclusive, and then find the complement to find the chance that that will not happen. So we're going to go to second vars. Mine is alpha B for the binomial CDF. We still have 10. We still have 0.3. Here the value in question is 5. So we're going to work out what that is. That is 0.9527. So then we want to do 1 minus that. And that is 0.0473. So there's under a 5% chance that that much blood will not be able to be used. So 0.0473, I believe. 0.0473. Okay. There's that one. It just occurred to me that this is about blood, and I happen to be doing this in red. All right, what's the number of usable pints will be? Exactly 5. So this is the probability. X equals 5. All right, so this is going to be the PDF, because when you are exactly equal to a number, that is what the binomial PDF is for. So we're going to go to second vars. Alpha A is where mine lives. We've got 10 trials. Success is 0.3, the probability. What were we looking at? 5, exactly equal to 5. Okay. So we're going to do the binomial PDF of 10.3 and 5. That is 0.1029. All right. There you go. That is that one. Oh, about a 10% chance that'll happen. The number of usable pints will be more than 4, but less than 8. And you notice they don't say it's inclusive. That will make a difference. So let's think about what this will be. This is going to be 4 less than X less than 8. That would be another way of saying, because this is discrete, we can't have decimal values here. That's basically another way of saying it's 5 less than or equal to X less than or equal to 7. And then we've seen this trick before. This is going to be the probability of X less than or equal to 7 minus the probability of X less than or equal to 4. So these are CDFs again. Second vars, we're going to go alpha B, where mine is. This is 10.3. And let's see, the first one is 7. That is 0.9984. I'm going to do store and put that in. Let's put it in C this time. Why not? So we're going to do alpha, and we'll pick this one over here and put it in C. Just to be different. Why not? Dare to be different. Let's see. And then we're going to do this all over again with less than or equal to 4. So second vars alpha B 10.3, and the number of interest is 4. You work that jazz out, you get 0.8497, and so now we're going to do alpha C minus second negative, the answer that we just got, and C minus the answer is 0.1487. Hey, how about that? I remember 1487. No, I don't. I would be over 500 years old if I remembered that year. Anyway, there you go, 0.1487. There's about a 15% chance that'll happen. What else do we have? What are the chances that all of the pints will be usable? Well, that's a mighty tall order, my friend, but okay. So this means we want the probability that X is, so all of them will be usable. So we want the probability of 0, basically. So you want the probability that the number of unusable ones is exactly equal to 0. And this is going to be a PDF. Okay, let's see. So, second bars, alpha A, there's where the PDF is. We got 10 trials. The probability is 0.3. The value in question is 0. We want no unusable blood whatsoever. There's a 0.0282 chance, or roughly a 3% chance. 0.0282 chance, roughly a 3% chance that will happen. What's the probability that none of the pints will be usable? All right, there's 2 ways you could approach this. You could do the binomial CDF for 10, but then, well, actually, so let's just do that. So none of the pints will be usable, which is another way of saying all 10 are unusable, which is what we've been measuring this entire time. So we want to find the probability that that all 10 of them are unusable. So let's see, let's do second enter. We're going to do pretty much the same entry here, except that this time this is going to be 10 instead of 0. And hit enter, that's 5.9 e to the negative 6. That is not very likely at all. 5.905 e to the negative 6. That basically means you're going to have 6 zeros, including 1 in front of the decimal point. One, 2, 3, 4, 5, 6, and then 5905. Because that, my friends, is scientific notation. And that's basically telling you that it's going to be well near impossible to have no usable blood at all. Find the expected value of the number of usable points. Okay, so that's another way of saying find the mean, which is n times p. And let's see, this time we're talking about usable pints. So usable is actually going to be 70%. So we need to switch our p-value and do 0.7. Up to now, we've always been doing 0.3 because we've been talking about it in terms of what is unusable. Just pay careful attention to the fine print. What is it you're defining as usable and unusable? What are you defining as success and failure? So for this, the number of trials is 10. The number of usables, the probability of usables is 0.7 or 0.70. So you multiply those together, you'll get 7. So on average, we can expect 7 usable pints. Find the standard deviation. Well, the variance, sigma squared, is going to be n times p times q. So this is going to be 10 times 0.7 times 0.3. Let's see, 10 times 0.7 times 0.3 is 2.1. And again, that is the variance. You want to find the standard deviation, which means you're going to do the square root of 2.1. The square root of 2.1 is 1.45 if you round it off. So that's the standard deviation. A coin is flipped so that there's a 57.7, or a coin is weighted so there's a 57.7% chance of it landing on heads. We're going to flip the coin 16 times. Find the probability that exactly 8 hit flips are heads, okay? So what do we have here? This means n, oh, for crying out loud. Come on. What are you doing? Why are you not drawing? Draw for me, I say. Draw. Thank you. N equals 16. That's the number of times we're doing this. P is the chance of heads. That's the success. So 57.7% is another way of saying 0.577. So what's the probability that 8 flips? So 8 is the number of interest. That's x. So we are going to do a binomial PDF because it's exactly equal to. And we're going to do, let's see, n is 16. The probability p is 0.577. And then the number of successes we want is 8. So let's grab our friendly neighborhood calculator and say, hey, calculator, go to second bars, go down to binomial PDF. I want 16 trials with a 0.577 chance of success. And I'm interested in getting 8 of those. So pray tell me, oh great and powerful calculator, bestow upon us humble mortals a sign of thine beneficence and kindness. Share with us, please, your divine wisdom, O great and powerful calculator. And it is 0.1621. Okay, there you go. I find it's good to be properly deferential and respectful of the power of the technology because I'm sort of preparing for the day when the AI becomes self-aware and begins trying to wipe out humanity. And I figure that if I show proper deference and respect to the machines, that maybe they will spare me and let me become like one of their lackeys, or maybe they'll turn me into one of those cyborgs they'll send back in time to murder people, and for some reason I'll have an Austrian accent for God knows what reason. So I'm kind of getting into the habit now of showing proper deference to the machines. So it's good to prepare. Anyway, where were we? So the probability is 0.1621. All right, what else do we have? So this time the coin is weighted, so there's a 64.6% chance of landing on heads. And so here you'll notice they actually want the chances of a tails. So this time Q, the chance it will not happen, is 0.646. Let's see, we're flipping it 13 times. That is n right there. Okay, there you go. We want at least 7. Let's see, P is going to be 1 minus Q. So if you do, what is 1 minus 0.646? That is 0.354 is what that is. And so you want it to be at least 7. All right, what does at least mean? That means 7 or smaller, which is another way of saying we want the probability that x is less than or equal to 7. And this is going to be a CDF. And this is still binomial because there's still 2 outcomes, head and tails. So it's a binomial CDF. The number of trials is 13. The probability of success is 0.354. And the number of the target value we have is 7 or smaller. So 7 is what we want, and the CDF is how we're accounting for 7 or below. Let's make that look a little bit more like a C. All right, so we're nearly done. Second vars, alpha B. The number of trials, I already forgot what it is. It is 13. The probability is 0.354. The x value is 7. And we work this jazz out, we get 0.9506. So that is 0.9506. So there's about a 95% chance that that's going to happen, that's pretty likely. Okay, so there you go. All right, so my friends, we have now completed chapter 6.